We have used Lagrange multipliers to find the maximum or minimum values of a function that has one constraint. As you can see, this problem has two constraints. The optimization function is f of x, y, z equals x squared plus y squared plus z squared. To determine the constraint functions, we first subtract 9 from both sides of the first constraint. So, g of x, y, z equals 2x plus y plus 2z minus 9. The second constraint function can be found similarly by subtracting 29 from each side. So we have h of x, y, z as our third constraint. Now that we have our constraints, we can calculate the gradients of f, g, and h. The gradient of f is 2xi plus 2yj plus 2zk. We have the gradient of g is 2i plus j plus 2k, and the gradient of h is 5i plus 5j plus 7k. We can now substitute the gradient values into the equation for delta f of x sub 0, y sub 0, z sub 0. Notice that this can be rewritten so like terms are together. We can now set the coefficients of I, j, and k equal to each other. We can combine these equations with the two that come from the constraints. We want to reduce the number of equations. Let's solve the second equation for lambda sub 1 and substitute this into the first and third equations. We now have 4 equations. Solve the first and second equations for lambda sub 2, set them equal to each other, and then cross multiply. This now gets us down to 3 equations with 3 variables. After solving this system of equations, we get x sub 0 equals 2, y sub 0 equals 1, and z sub 0 equals 2. Substitute these values into the original function, x squared plus y squared plus z squared. This gives us 2 squared plus 1 squared plus 2 squared, which equals 9. So, f of 2, 1, 2 equals 9 is a minimum of the function x squared plus y squared plus z squared, given the two original constraints.